Let's look at an example dealing with pressures instead of concentrations. If I2 has an initial pressure of 1 atmosphere, what are the equilibrium pressures of I2 and I? We're given our balanced chemical equation and the value of Kp. Just like we have for other equilibrium problems, we're going to set up an ICE table. I for initial, C for change, and E for equilibrium. I know my initial pressure of iodine is 1.00. There's no mention of atomic iodine, so I'm going to assume that the pressure of that is 0. Now for the change row, I have to use my coefficients for my balanced chemical equation, and in doing so, I'm going to lose some of the I2, and I'm going to gain I, but I'm going to gain 2 times the amount of I because of the 2 in my balanced chemical equation. For my equilibrium, I simply add up the initial and change rows, so I have 1.00 minus x and 2x. So now I have my equilibrium values with respect to x, my equilibrium pressures with respect to x. Now I can set up my Kp expression, so I know that Kp equals the pressure of iodine, elemental iodine, squared over the pressure of I2. Now I can substitute in the values I know. I have 2.91 times 10 to the minus 4th for my Kp value. That's going to be equal to the pressure of iodine, which note that is 2x. I still have to square that because the pressure is 2x. The law of mass action tells me that whatever that term is, it must also be squared. Note that the square does go outside the parentheses so that we square both the 2 and the x. That's a common mistake that students make. And on the bottom we have the pressure of I2, which is 1.00 minus x. And we're going to again make our simplifying assumption that x is much, much less than 1.00. And when we do, we can write out 2.91 times 10 to the minus 4th equals, what we'll have is 4x squared. We could show the 1 in the denominator, but it doesn't change the value in our problem, so we're going to leave it out. Now I can divide both sides by 4 and take the square root, and when I do that, I find that x equals 8.53 times 10 to the minus 3rd. Now I can use this value of x to find my equilibrium pressures by substituting this value back into what I have in my equilibrium row. And what I find is that the equilibrium pressure of I2 is equal to 0.991, and the equilibrium pressure of elemental iodine is 0.0171, and these are both in units of atmospheres.